Today we're going to look at section 4.4, which is all about exponential and logarithmic equations. So our objectives today, we're going to use like bases to solve exponential equations, and we're going to use logarithms to solve exponential equations. So an exponential equation, it's going to be an exponential equation is an equation containing a variable in an exponent. Okay, so if you have a variable in an exponent within an equation, that's what we're dealing with. So looking at this example, 2 raised to the 3x minus 8 power equals 16. We have an x, a part of the exponent. So all exponential functions are one-to-one. Remember, that means that no two different ordered pairs have the same second component. All right, so how do we solve exponential equations? Well, there's several different types of exponential equations, and here's one situation. If b to the power of m equals b to the power of n, so as long as we have the same base on either side, what we'll do then is we get to ignore the base, and we get to just set the exponents m equal to n. Okay, but we have to have the same base in order for us to just set the exponents equal. So we are going to rewrite the equation into that form if we don't already have the same base. Okay, so if we do have the same base, we can skip this first step. If we don't, then our goal first is to get the bases to be the same. Now, understand that we can only take a base and make it a smaller number being raised to something. I can't take a base and make it a bigger base, okay? So we can only go smaller numbers for bases if we want to get them the same. But then we would just set our exponents equal to each other, and then we'd solve for the variable. Okay, so looking at this problem, we want to solve 5 raised to the 3x minus 6 power equals 125. Okay, so notice as of right now, on the left-hand side, we have a base of 5. And on the right-hand side, we have a base of 125 because technically that 125 is raised to the first power. So unfortunately, we do not have the same base, which means we cannot just set our exponents equal to each other. Like I mentioned, we can only go from a big base to something smaller. So I'm not going to be able to change the 5 into 125, but hopefully we notice that 125 is going to be able to be a base of 5. So 5 to what power gets me 125? So you're thinking about having to multiply that by itself as many times. Well, hopefully we recognize that 5 to the third power is going to get me 125 because 5 times 5 is 25, and then 25 times 5 is 125. All right, so notice how I was able then to change that to a base of 5, and now since they both have the same base, I can just focus on the exponents. So 3x minus 6 is going to equal 3, and now I can start solving for x. So I'm going to add the 6 over to the other side. That gives me 3x equal 9, and then we'll divide by 3, and so we get x to equal 3. And like I mentioned in the last slide, so once again, if I go back here, oops, it was actually this one, because we're dealing with one-to-one functions, that means that we know that 3 will be our answer, okay? So it's unlike some of the other situations like we've done in the past where you'd have to check your answer to make sure that it is a solution. Here, if we're dealing with exponential equations, the answer that we get will be our answer. All right, let's take a look at this one. We want to solve 8 raised to the x plus 2 power equaling 4 raised to the x minus 3 power. So notice that right off the bat, I see that one of my bases is 8 and one of my bases is 4. So unfortunately, they do not have the same base. So we're going to have to get the bases to be the same in order to set the exponents equal. So remember, I can't turn the smaller base into the bigger one. So right now, it looks like I want to try to turn 8 into a smaller base. Well, if you can, we would want to ideally turn it into a base of 4. But remember, I'm asking myself then 4 to what power is going to get me 8? And that's just not possible. 4 to the first power is 1. 4 to the second power is already 16. So we missed that. So that means that we actually are going to have to change both of these bases to an even smaller number. Hopefully we notice that, hey, 4 is the same thing as 2 squared, and 2 to the third power is going to get me 8. Now, here's the thing. If I change the 8 to 2 to the third power, it's still being raised to the x plus second power. And because I'm turning 4 into 2 squared, that's still being raised to the x minus 3 power. So here is my new equation. Now notice that they have the same base of 2, but inside the parentheses, there's another exponent now. So if you think back to your properties, when we are dealing with a power raised to a power, we have to remember that that means multiplication. So because the bases are now the same, I can ignore the base of 2, but I have to think of this as 3 times x plus 2, because a power to a power means multiplication. And that's going to equal now 2 times x minus 3, because once again, power to a power means multiplication. But now I can go ahead and I can start solving for x. So I'm going to have to distribute the 3 on the left. I'm going to have to distribute the 2 on the right. So we'll have 3x plus 6 to equal 2x minus 6. So what I'm going to do is I'm going to move the 6 from the left over to the right. That will give me 3x to equal 2x minus 12. And I'll move the 2x over to the left by subtracting. And so that's going to get me x to equal negative 12. Once again, because these are one-to-one functions, I know that my answer that I get for x is going to work. I don't have to worry about checking it. We obviously could if we wanted to, but it's not really necessary. Okay, so once again, sometimes you might have to change both bases, but make sure that if you change the base, it has to be to something smaller. And then if you end up with a power to a power, we're thinking multiplication. So pause the video and see if you can solve this equation. Okay, hopefully you noticed that the bases were different, but I can very easily change 27 into a base of 3. It'd be 3 to the third power, but then that 3 to the third power is still being raised to the 2x power. So a power to a power, I had to multiply. So x minus 7 equals 6x. And then notice that I had to divide both sides by 5. It didn't turn out to be the prettiest number, so I just left it as that reduced down fraction, so negative 7/5. All right, so here's another way of solving exponential equations, because not every exponential equation we're going to be able to get the same base on each side. Okay, if we can, that's really the most convenient way, but sometimes we can't. So what we do when we can't get the same base on both sides is we're going to use the natural log to solve exponential equations. Remember, natural log is that ln button. So using the natural log to solve exponential equations, here are the steps. We are going to isolate the exponential expression. So any number that is on the same side as the exponent term, but is not attached to the exponent or the base, we got to move it to the other side. Then we're going to take the natural log on both sides of the equation, because if you do something to one side, you got to do it to the other side to keep it balanced. So step 3, we're going to simplify using one of the following properties. If we have the natural log of b to the power of x, we're going to use the power property, where notice then that exponent gets moved out in front, and then it becomes x times the natural log of b. But sometimes our base might actually be the number e. And so if that's the case, natural log and e, those are inverses of each other. So those would end up canceling out, and that's why it would just equal x. So 2 scenarios depending on what kind of base we have. If it's not a base of e, we're going to use that power rule. If we do have a base of e, then we have inverses. And then once we have that, we don't have any more exponents, and so then we can solve for the variable. All right, and so this is going to involve using a calculator because we don't know the natural log of numbers off the top of our head. So notice that the directions say to round to 2 decimal places. So we're going to solve 5 to the power of x equals 134. So hopefully you notice that the bases were not the same. 134 is not going to be able to turn into a base of 5. So that's why we have to use the calculator. So because 5 to the power of x is completely isolated by itself, we don't have to do any extra steps to get that by itself. So that means that we get to move on to the step where I'm going to take the natural log of both sides. So I'm going to take the natural log of 5 to the power of x, and that's going to equal now the natural log of 134. Because my base on the left is a base of 5, natural log and 5 are not inverses of each other. So we're going to use that power rule, and we're going to move the exponent out in front. So it's going to be x times the natural log of 5 to equal the natural log of 134. Now to get the x by itself, because x is being multiplied by the natural log of 5, to undo multiplication, we are going to divide. So we're going to divide both sides by the natural log of 5. So that's going to get me the x by itself. And now this is where we're going to very carefully type this into our calculator. So remember, hit the natural log button, do 134, close the parentheses, then divide by the natural log of 5. And rounding to 2 decimal places, we are going to be getting 3.04. All right. Once again, because this is an exponential equation, we don't have to check our answer to make sure that it is a solution. It will be a solution. Okay, so it's approximately 3.04, which 5 to that power would get me 134. Okay, let's take a look at this example. We're going to solve 7 times e to the 2x power minus 5 to equal 58. Once again, we're going to round to 2 decimal places. Okay, so because we do not have our base by itself, okay, this is what we want to get by itself. We have a 7 and we have a negative 5 on the same side. So our first step is we have to isolate to get that e to the 2x power by itself. So following the rules for solving an equation, I'm going to add the 5 first. That's going to give me 7 times e to the 2x power, and that's going to equal 63. I'm going to then divide both sides by 7, and that will get me my base by itself. 63 divided by 7 is 9. Okay, so now that we've isolated the base by itself, I'm going to take the natural log of both sides. All right, notice that because we have the natural log and then a base of e, these are inverses of each other, and so those are going to cancel. That's going to just leave you with that exponent of 2x. This still equals the natural log of 9. And then the last step is to divide both sides by 2. Remember, when we are dividing, we'll do the natural log of 9, close the parenthesis, and then divide by 2. So rounding to 2 decimal places, we should be getting 1.10. Okay, if you are not getting these numbers in your calculator when you're following along, please reach out to me so we can figure out what's happening with your calculator. Okay, but that should be your answer. Okay, so pause the video and see if you can solve this equation. Once again, round to 2 decimal places. Okay, we had to isolate that e to the negative x power. So I subtract 9 first. I divide by negative 5, and that turns that fraction positive. Then I took the natural log of both sides, giving me a negative x equal the natural log of 3/5. I divided both sides by a negative, and then I typed it into my calculator. So a negative, then natural log of 3/5. And then I rounded to 2 decimal places, which got me 0.51. So that's us using like bases to solve exponential equations and using logarithms to solve exponential equations.